Hey there, folks. Let's work the problems that we worked in class this morning. I want to go through them. I could tell a few people were having a shady understanding of what we were doing with some of these problems. So let's go through them. And I'll do my very best to explain them in an obvious way. So if we are, we're going to start with problem 5. We did 3C in class, but I actually did that as part of the last homework set that I did. And wasn't thinking that we didn't do it, but that's fine. It's on the record, and you can watch that in the previous lecture. Let's start with number 5. It says define a function from the natural numbers to natural numbers by f of 1 is 1, and for all other natural numbers, f of n is the sum of the factors in the prime factorization of n. So you take the prime factorization, these are the primes that you multiply together to get n. The function value would be, okay, don't multiply, but add. And so, for example, f of 242, which is 2 times 11 times 11, that would be 24, because you add 2 and 11 and 11. So the question is this function one-to-one? Is it onto? Well, I can tell you right off the bat, let's tackle the one-to-one question. That it's not. And the reason I can say that is you can take a lot of numbers and write them as a sum in different ways. Okay? For example, 6 is 2 plus 2 plus 2. It's also 3 plus 3. Okay? So that kind of gives me my counterexample. There's several. I think we had a different one in class, but the counterexample that I would throw up here is note that f of 8, now this is 2 times 2 times 2, would be 2 plus 2 plus 2, which is 6, and that f of 9, which is 3 times 3, is 3 plus 3, which is 6. So those are equal, but 8 is not equal to 9. Okay, so there's your counterexample. If they were one-to-one, if I get the same answer, f of whatever, I get the same number, then that whatever it is has to be equal to the other whatever it is. Okay? Now let's tackle onto. Now remember what we mean by this is, can I take any natural number over here and map it back to a number whose prime factorization, instead of multiplying, adds up to my number. Okay? For any n that's in, maybe I shouldn't use n because we used it up here. Let me use m. How about that? For any m that's in the natural numbers minus 1, we can write m as a sum of 2's, and that's if it's even, right? Or as a 3 plus several 2's. And that's if m is odd. So the element of the natural numbers x such that f of x equals m is just the product of these things instead of the sum. 2s and or 3s. Thus, it is onto. Okay, and that's what that little proof looks like. Okay, does that make sense? No matter what you give me, if it's even, and we're talking about 2 and bigger, right? So I can either say, all right, there's a bunch of 2's here, but it's an even number, and then if there's 12 2's, you know, it's 24, there's 12 2's, then I can map 2 to the 12th to 24, right? And if it's odd, just replace one of the 2's with a 3 and go on about your business, right? Okay, so that's 5. Let's take a look at 6. 6 was weird. It says, okay, let's define a function that maps from R2 into R2 by taking the new first coordinate will be the sum of the first and second coordinates. The new second coordinate will be the product of the 2 coordinates. So the question is this onto? All right, well, let's think about this. Let's consider a general point in R2, xy, and solve for a and b such that, and these have to be real numbers, such that f, and it's kind of weird that they're doing the double, but I mean it's accurate because what we plug into this is a point, but a lot of times when the parentheses are redundant, they'll just drop one set of parentheses, equals xy. Okay? Then what we have here is a system of 2 equations. We've got a plus b equals x, and we've got a times b equals y. And now it's probably easier to go ahead and solve for either a or b in the first equation and then plug into the second. So I'll follow the tack that we used this morning. I think we solved for a equals then x minus b. And then we take this and we take this and put them together. So this means that b times, I guess I'm doing them in the wrong order, but b times x minus b equals y. Okay? And this means now that I've got bx minus b squared equals y. And let me take everything over to this side and then switch sides. So this is b squared minus bx plus y equals 0. And remember, b is what I'm trying to solve for, not the x, not the y. I want to solve for b in terms of the x and y. This has real solutions when the discriminant, that's what we typically think of, it's ax squared plus bx plus c, then that's b squared minus 4ac. Now in this case, my b term, if you will, is the negative negative x squared minus 4. A is still 1, and my c here is the y. Is greater than or equal to 0. So this is x squared minus 4y greater than or equal to 0. And x squared greater than or equal to 4y. And the way we typically see this is y is less than or equal to x squared over 4. So if we're drawing this, it's going to reduce things down. 2 would typically give us 4, but then you divide by 4, so 2 is going to give us 1. So this is going to be a very flat-looking parabola. It's kind of squished down by a factor of 4. And this is only going to work in areas where the y is less than this curve. So down here, we're okay. Okay. But if 1, let's see, x was 1 and y was, I don't know, 3 or 2, it doesn't matter. All right, if x is 1, then this is 1/4, y would be 1/2, right? No, I'm sorry, it would be 1/4, right? So take anything up here, and we won't be able to solve for a and b that make that happen. Okay? So this is not onto. Thus, f, and I'm kind of doing things out of order, I'm sorry, but I'm out of space, is not onto, since some points, cannot be made with real a and b. Okay. Okay. Now, is it 1-to-1? Well, this one is a little obvious. No. Since. And you can choose anything, but you got to look here and realize that addition is commutative, multiplication is commutative, so f of 2, 1, for example, would give us 2 plus 1 and 2 times 1, which is 3, 2. And then f of 1, 2 is 1 plus 2 times 1 times 2. So this is 3, 2. But 2, 1 is not equal to 1, 2. Okay. So 1-to-1 is wrecked on that one. Now, if we wanted to, okay, I think we could fix this, and that's the second question. It says find a maximal set S on the domain such that the restriction onto that is 1-to-1. And I'm just trying to think if there's any. If I put the negatives in, I get a different thing. The real thing is I have to get rid of this symmetry thing, right? What's happening here when we do this is we are flipping over this diagonal line, which is what we do when we take the inverse, correct? We flop over this line. So what I need to do is take one of these half planes, either the one below or the one above, and let S be the set of, I don't know, AB, such that A is always less than or equal to B, for example. A, B, real numbers. Okay. So whatever x is, well, actually I ends up taking the one above. It looks like here, if x is whatever x is, I'm taking the y above the x. So, or I could do it the other way. I could say let A be strictly greater than or equal to B. All right. So anyway, but either one of those will eliminate this business of turning it over, right? 1, 2 would be in the domain, but 2, 1 would not. okay, then F restricted to S is 1 to 1. Okay, I couldn't pull that little flip it over thing like I did before. All right, so that is 6. Let's take a look at 9, which says, all right, show the composition of functions is associative. That is, if F is a function from A to B, G is a function from B to C, and H is a function from C to D, show that H of the quantity G of F is equal to the quantity H of G composed with F. Now, the real thing that's happening here is that we're using function notation instead of relations the way we used to. We used to talk about ordered pairs being in relations. And we actually proved this very thing with relations, right? I think it was 5.1, number 12. We said, all right, if we can pose relations, that we had this kind of associativity of the composition. Well, functions are relations. So really, we could just say, there's a one-line proof to this if we want to use it, saying that, oh, well, if, no, we say since these are all relations, then go look at the proof of number 12 and 5.1, and that would work. But I think what they really would like for us to do is to go ahead and restate this with the function notation. So let's do that. Okay, now these are still sets. You got to remember, these are sets of points, right? They're going to start with A, and they're going to end with points in set A. They're going to end with things in set D. And it doesn't matter how you do this, that's what's going to happen. But we have to show that if we have a point, since they're sets, we have to do the double set inclusion. If this is a subset of this, and then later if this is a subset of this, then that means they're equal. Okay? So that's what we're setting out to show here. So let's see if we can do that. So let's start by saying, all right, let A be an A and D be something in the set D, such that if I take H of the quantity G of F of A, then that gives me D. Now basically what we're saying there, I mean, if we go back to our relation proof, we're saying that the ordered pair AD is in this function. Okay? Well, if we compose things and get from one end to the other, I start with A and I get all the way over to D, this composition means there was something in between, right? So then there exists, and H actually starts with C, so I'm going to use a lower c as little c, that's an element of big C, such that two things happen, right? I've got to take G of F of A and hit that C, and then I've got to take H of that C and get to D. Okay? That's what composition means. It means there's something in between that I hit, and then when I compose, I just skip right over it. Okay? But now let's focus on this. F goes from A to B, G goes from B to C. So then there exists some B, little b, in the set B such that F of A hits this B, and then G of that B is C. Okay, so we've got it broken down pretty well. So now let's look at what we've got here. To show that it's in the other set, I need to say, all right, F is going to take F of this A, and what I've got to show is this ordered pair AD is in this set, which means I take, the function value of A and get D. Well, let's think about what this means. Since G takes B to C, and H takes C to D, then H of G of this B, B goes to C, C goes to D, equals D. And then F of A goes to B, this goes to D, so then F applies to, takes A to B, and then this takes B to D. So what I've shown is that this ordered pair, which I took to be in this subset, is in this subset. Thus, H of G of F is a subset of H of G quantity of F. Okay? Alright, then we do it the other way. Now, let A be an element in A, and D be an element in D, such that H of G, okay, composed with F of A gives me D. Okay, what this is telling me then is there's some middle ground, some element in between the set A and the set D, right outside of F here. Then there exists a B in the set B such that F of A goes to this B, and then H of G picks up this B and takes it to D. And so then there exists some C in the set C such that G takes B to this C, and then H picks up that C and takes it on over to D. So let's see if we can do the crosswalk now this way. G of F would take, let's see what I know, F takes A to B, and then G takes B to C. So then G of F of A, F takes A to B, G takes B to C. This goes to C. Then G of F takes it to C, and H of C takes it to D. So then H of G of F, okay, starts with A, goes to C, and then H takes C to D. Thus, H of G quantity of F is a subset of H of G of F. One last sentence, right? Therefore, since this is a subset of that, and that's a subset of this, H of the quantity G of F equals H of G quantity composed with F. Okay, and that is it. That's what we had to show. Okay? It really is, when you go back and look at the proof with relations, it really is the same proof. It's just we're using slightly different notation. Okay? And then the last one I'll do in this little segment, and then we'll jump into, actually that's not true, I think I want to do a couple more. No, let's see, 12 and 13 are left, they each have two parts, so I'll do this last one. It says, okay, if let's prove that if a is a function, if f is a function from a to b, and g is a function from b to c, and they're both onto, f is onto b, g is onto c, then we need to show that g of f, which goes from a to c, right, starts with this, goes to that set goes to here, that this is onto. Okay. So remember how we show onto. We take just a general element in the codomain. So consider a general element C in the set C. Okay, nothing special about it, just there. Okay? Since G is onto, okay, I know there's some element here in B that will give me this element C. So since G is onto, then there exists a B in the set B such that G of this B gives me the C. Okay? But f, which is a function from a to b, is onto the set B. So since, same trick, right? Since f is also onto, then there exists some, I'll call it little a, in the set A, such that if I took f of this A, I would get B. Okay? Then look at what we have. I've got f taking A to B, and then G taking B to C. But more than that, well, that is the point. So that now I've got this composition that takes f of A to B to C. Okay? And that means then that G of f of this A goes first to B, then B goes to C. And so what I've done is I've taken a general element in C and shown that there has to be an element in A such that G of f of that A gives me C. Thus, G of f is onto. Okay, all I had to do was take a general C and say, hey, can you show that there's something back here that would give me that? Okay, and you can. All right. All right, so I'm going to stop right there. We've got 4 more little problems, 12A, 12B, and 13A, 13B, that we'll do after this. I need to run an errand, actually, and then I will be back and we'll take care of that. So let me exit this.